This is a review worksheet that allows us to practice through all the tests that we've seen, convergent tests that we've seen from 9.1 through 9.6. So we want to find the best test to use to determine convergence or divergence, and we can save a lot of time if we're able to follow these guidelines that can help us produce an order that we can use to test these convergence and to test whether a series will converge or diverge. So the first thing that we always do is we always do the nth term test and make sure that that it is not something that we can just catch with the nth term test. So remember, nth term test will only test for divergence, or it will be inconclusive test. So if the limit as n approaches infinity for our rule of sequence will produce anything other than 0, then we know it will diverge. If it does approach 0, then we know the series is the convergence is inconclusive. Okay, the next thing we can usually look at the rule of sequence and decide, is it in the form of a geometric, meaning that I have a ratio raised to a variable. If it's a p-series, where I have a variable that is raised to a constant, or is it telescoping, where we have terms that are eventually going to cancel each other out and reduce. Okay. The next thing to consider is the series alternating. If we see that's alternating series, then obviously we use AST, alternating series test. If the series is closely related to one of the special series, maybe it looks like it looks closely related to a geometric, a p-series, then we can usually use the limit comparison test. I think direct comparison test will probably be something that is maybe a little bit more involved to use. So maybe limit comparison test would be the preferred method, especially if we're having something that is looking similar to the p-series. Okay. If the terms are raised to an nth power, then we could use the root test, especially if we see cube root or fourth root or nth root. If the series can be integrated easily, then we use the integral test. And if nothing else works, then we use the ratio test. So this is kind of like a catch-all. Usually the ratio test is going to probably be the one that you are going to use more than the root test. I think root test you can usually tell by looking at if you see a root in the original rule of sequence. All right, so putting it all together, determine if the following series converge or diverge. We want to name the test and the criteria of each test used. So the first thing we always do is nth term test, and this one, with the nth term test, the limit of our rule of sequence will go to 1/4, and since the limit doesn't equal to 0, we know by the nth term test that the series will diverge, so that's an easy one to catch. With B, we see that this is in the form of geometric series. We have a ratio raised to a variable, and we see that this ratio is 2/7, which is less than 1. So therefore, we know by the geometric series test, the series will converge. Part C, this is in the easy form here. This is matches the p-series exactly, and we see that this p-value of 3 is greater than 1. So therefore, we know this is going to be a convergent series. Here we have n squared over 5 to the nth. We know that an exponential function is going to grow at a faster rate than n squared. So we could, if we tested the nth term test, the denominator is going to grow faster. So we know limit is equal to 0. So nth term test is inconclusive. And anything that is involving exponents, usually we can do the ratio test. So ratio test, we find the limit as n approaches infinity for the n plus 1th term divided by the nth term, or by the rule of sequence, and replace all the n's with n plus 1s, and dividing by a fraction, the same thing as multiplying by its reciprocal. So when we do that, we see a lot of these terms are going to naturally cancel out. And if we apply the limit as n approaches infinity, we see all these values cancel out, leaving us with just 1/5, and 1/5 is less than 1. So therefore, by the ratio test, we know this series will converge. All right, so next one here, 1 over cube root of n to the 5th plus 5. We see that this rule of sequence matches with the p-series, and we see a root here. So we know that we can, we can use the limit comparison test, because especially if something that is similar to the p-series, that's what we can use. So so this resembles like a parent graph of 1 over cube root of n to the 5th. So we can find the limit of the original sequence over the simpler rule of sequence. And when we do that, again, multiply by the reciprocal. And if we find a limit as n approaches infinity, this equals to 1. And since this resulting limit is finite and positive, and we know that the simpler series will converge by p-series, because this is p is going to be equal to 5 over 3, greater than 1, then we know by the result that the series will converge by limit comparison test. Okay, for f, we see that this is in the form, first the nth term test is going to be inconclusive. The denominator is going to increase at a rate so that the limit will be 0. So then we look to see maybe this we can use the integral test. And if we think about these values for n is greater than 2, we know this will be positive, will be convergent, will be positive, continuous, and decreasing. So if that's the case, we can use the integral test. So integral test, we can let the u value be natural log of n. We find the derivative, which is 1 over n, and 1 over n will help cancel out this n in the denominator. And once we have that, we have 1 over u to the 4th and 1 over u to the 4th. Bring this up to the numerator, and to allow us to use power rule, u to negative 3 over negative 3, we find a limit as b approaches infinity for this integral from 2 to infinity. And when we plug b into our integral, or our resulting function, we're going to get 0, because this, as n approaches infinity, this fraction will produce 0 minus negative 1 over 3 natural log of 2. So this will be a positive finite value. And because our integral produced a positive finite value, we know the rule of sequence, the series, will also be convergent. All right, so here we can first try the nth term test. If we do the nth term test, we see this will go to 0. So therefore, nth term test is inconclusive. This is basically, we can use limit comparison, because we see that this, if we compare the degrees between numerator and denominator, we can think of this as a more complex version of 1 over n. Okay? And we can compare this, do a limit comparison test with 1 over n. We know 1 over n diverges. So we put the original sequence over the simpler sequence, multiply by the reciprocal, and we're left with 5n cubed minus 6n squared plus 3n over n cubed minus 7n plus 8. And if we find a limit as n approaches infinity, this will produce 5 over 1. And 5 over 1 is finite and positive, so we know that this test will work. And since 1 over n diverges, we know that this series must also diverge as well. Okay, for h, cosine of n pi. Cosine of n pi is just a fancy way of showing alternating values between negative and positive. If I plug in n is equal to 1 and then go to 2 and 3, 1 pi, 2 pi, 3 pi, it'll cause this value to alternate between positive and negative. So we can just think of this as negative 1 to the nth power over square root of n. So we can use the alternating series test, which basically says that if the limit as n approaches infinity for our rule of sequence, in this case 1 over square root of n, is equal to 0, then we know this will converge. All right. So this will converge by the alternating series test. However, without the alternating series, without this alternator, this 1 over n to the 1/2 will fail because this 1/2 is going to be is not going to be decreasing fast enough, because we're using p series. We know that 1/2 is less than 1, so therefore the series would diverge if it were not for this alternator. So because this requires the alternator for this series to converge, we can say that this series converges conditionally based on the fact that it needs the alternator in order for it to for the series to converge. All right, we have 3 to the n plus 4 over 2 to the n. If we use the nth term test, we see that 3 to the n is going to increase at a much faster rate than 2 to the n, and so therefore this will diverge by the nth term test, since the limit of the sequence does not equal to 0. It will go to infinity. And for j, we see that this nth term test will produce 2/3, and it will produce 2/3, and 2/3 does not equal 0, so therefore the series must diverge. Okay, not converge. The series diverges.